Hey everyone! Thank you so much for watching another episode of the Weaviate podcast. I'm super excited to welcome Magdalen Dobson to the Weaviate podcast. Magdalen is one of the world's top scientists in Approximate Nearest Neighbor Search, the core technology underpinning vector search and vector databases. Magdalen is currently finishing her PhD at Carnegie Mellon, where she's led a research effort, ParlayANN. This is such an exciting study that we'll be diving into throughout this podcast. Magdalen, thank you so much for joining the Weaviate podcast. It's such an honor to have you.
Oh, thank you. It's great to be here.
Awesome. So I'm so curious about this, and this recent experience of seeing your talk at MIT, and I was so curious about this background of you did your undergrad at MIT, and then you come to Carnegie Mellon, and I'd really just love to learn the journey of what led you to Approximate Nearest Neighbor Search Science.
Yeah, absolutely. Yeah, so I got my undergrad at MIT in math, but even as I was a math undergrad, I was starting to get very interested in computer science. I took a lot of computer science courses, and I ended up applying to PhDs in computer science. So I started my PhD at Carnegie Mellon with Guy Blalock, who works I would say, at the intersection of theory and practice in the area of parallelism and concurrency. So I sort of came at this from being very interested in developing parallel algorithms, particularly algorithms for like building and updating data structures in parallel. I'd say that's something I'm very, very interested in.
Hmm.
And I guess how I came to Approximate Nearest Neighbor Search. So my advisor had suggested my second year of my PhD that we should do a project on low dimensional nearest neighbor search. So we did this project in low dimensional nearest neighbor search where we looked at building and updating KD trees, which are a type of space splitting tree that work very well for very low dimensional nearest neighbor search. So here right now I'm talking about dimensions in the range of like 2 or 3. So not stuff that you would do on like vector embeddings or anything. But we did this project. I had a really good time. And I guess we just thought to ourselves, okay, this method works really well in low dimensions, but like let's see what's up in high dimensions. And this would have been around 2021 or so. So a lot of the advances in approximate nearest neighbor search in the form of graph-based algorithms were really starting to come on the scene, starting to become like a lot more mainstream. And, we started doing some reading. We read about all of these partition-based methods like locality-sensitive hashing. We read about algorithms like DiskANN and HNSW. And we really felt like there was probably a lot that we could say about the parallelism of building these graph-based approximate nearest neighbor search algorithms. So that was sort of how we became very interested in looking at this problem.
It's so exciting. I think this combination of your expertise in parallel computing, concurrency with ANN algorithms, I think is so unique. And maybe like that's been kind of my experience with Weaviate and, looking at the code and seeing how HNSW is implemented is I see all this locking and, I didn't have much of a background in that, but coming into Weaviate. And I guess the work is about getting rid of those locks and we'll get into that as well in a second. So, and then also kind of that KD trees, hearing that evolution from say like Annoy and hearing how the evolution over time as you expand the dimensionality. I think all that is so interesting as well. Awesome. So could we dive into ParlayANN?
Absolutely. Yeah. So I guess I mentioned earlier that we were super interested in learning how to parallelize these approximate nearest neighbor search algorithms, particularly the graph building ones. And where we came at it is we noticed looking at, diving into the actual code for these algorithms like DiskANN and HNSW, we did notice that there were a lot of locks used in a way that perhaps, you might say that in a way that like an expert on parallelism would really not see as all that necessary or that would really want to get rid of. And they did, I don't want to like put them down. They worked quite well on like, 32 core, maybe up to 62 core machines. But when we were testing them on, for example, we have a lab machine that has about 200 cores. And when we were testing them on such high thread counts, it really did become quite evident that there was too much contention coming from the locking. So we in ParlayANN, we set out to get rid of that. And yeah, I'll say like a little bit more broadly, ParlayANN sort of had two goals. One goal was to parallelize these graph-based nearest neighbor search algorithms without locks. And I guess the one of the broad goals there was to look at a wide variety of methods for building these graphs. So we chose four algorithms to be our topic of study in ParlayANN. So we chose DiskANN and HNSW, which will probably be, familiar to a lot of people listening. We also chose another algorithm called HCNNG, which is based on a hierarchical clustering decomposition. And then we also chose another algorithm called pyNNDescent, which is based on an idea of iteratively refining a nearest neighbor graph by looking at neighbors of neighbors. So the goal of this one would be to build sort of a k nearest neighbor graph for k equals 40. So we on purpose tried to pick a lot of techniques that we saw as very diverse, partially because we wanted to see about how they compared against each other, and also because that provided a lot of different avenues for looking at the parallelism.
Amazing. So, can we maybe start off by unpacking the lock contention a little further, and then we'll dive deeper into HNSW, DiskANN, HCNNG, and pyNNDescent. So
Yeah.
this kind of maybe to set the stage for our listeners, locking is you have multiple threads and they share some kind of resource. So one thread locks it, so the other can't access it.
Hmm.
And so, can you maybe clarify, what lock indeterminism is, why it's a problem?
Yeah. So I'll start by saying the minimum about how some of these algorithms work.
Oh,
So we can start with DiskANN. So DiskANN is an incremental algorithm, which means that sequentially it would just be built by calling the insert procedure over and over. And at the highest level, how the insert procedure works is you have a point P that you want to insert into the graph, and you go and identify the edges that you want to form. So you form edges P to V for some subset V of existing vertices. And this is a directed graph. So you also need to add edges from those vertices V back to P. And this is the part where you could have what's called a data race. So imagine you were doing this in parallel. You could just imagine you're doing a for loop where each insertion is doing its work independently. If you were doing this in parallel, 2 points P could be trying to add themselves at the same time to the neighbor list of some already existing vertex in the graph. And this would cause this, in C++ or most languages, this would cause undefined behavior. And so all sorts of terrible things could happen. And the sort of most simple or traditional solution to get around this is with a lock. So a lock would be something that one process would use to say, hey, I own this piece of data, I'm modifying this piece of data, nobody else is allowed to touch it. And the thing with locks, especially in C++, is that if two processes are trying to access something at the same time, there is indeterminism in which lock will acquire the vertex first. And because of the way these algorithms work, they're not sort of history independent. They don't just depend on the vertices that are in the graph. The order in which the vertices are inserted does actually affect the out neighbors of every vertex. So because of this fact, the lock indeterminism does actually cause non-determinism in the actual graph structure itself.
Amazing. It's such an interesting coming into the details of how these systems are actually implemented. And so I think maybe we could even come back to this kind of ordering. I know you had notes on, say, adversarial ordering of nodes. And then as we talk about batch construction, we'll get further into the ordering of nodes and how they're inserted into these graphs. But maybe before we go a little further into parallel index construction, would you maybe mind explaining further about how HCNNG works and pyNNDescent? Because I think our audience is probably pretty familiar with HNSW and DiskANN, but I think these other two algorithms are a bit less explored.
Absolutely. Yeah, so I'll start with pyNNDescent actually, because I think that's a little easier to explain. So the idea of pyNNDescent is that you can start with a graph that is not that great, So maybe I've run, you don't need to think too hard about how we got this ANNS graph that's not that great. You could imagine maybe we ran DiskANN with like some very small parameters, or, other methods like some
Hmm.
extremely approximate sampling, something like that. But yeah, we start off with a graph that's like not all that great, and we want to refine it. And the idea of pyNNDescent is that if you have a graph that is okay, and you have some vertex v, and you want to get you want to get better neighbors for it, the idea is that the neighbors of its neighbors are likely to be good candidates to be a neighbor.
Yeah.
So how pyNNDescent works then is that you start with this graph that's just okay, and on in a bunch of rounds for every single neighbor, for every single vertex, you look at all of its neighbors of neighbors, so it's sort of two-hop neighborhood, and you consider those as possible edges to replace the current edges of that vertex.
Mhm.
And then you keep doing this procedure over and over again until only a small fraction of the total number of edges in the graph change on each round. So typically, like in my experience, it's been about 10 or so rounds.
Could we maybe so HNSW has this like distance pruning. I love the analog you draw of the long edge of triangles. So and then I read about this in ACORN, this kind of two hop. If you keep the two hop neighborhood, you have more like expressiveness from each node. Could we maybe dive further into? I know maybe it's a tough one to just think through. I'm sure you're capable of it though. Thinking through the difference between this kind of HNSW pruning with this kind of like two hop neighborhood heuristic.
Mhm. Yeah, so pyNNDescent, their goal is really to build like a k-nearest neighbor graph. And by a k-nearest neighbor graph, I mean a graph where over your data set, the edges that a particular vertex forms are to its, say, 40 nearest neighbors in the data set.
Hmm.
So this is this I talked, I guess, in my talk about how HNSW and DiskANN really try to have a lot of diversity in their edges, and I think it works very well for them. They try to have edges that go out in a lot of different directions, and a variety of edge lengths. And this is actually, this is maybe kind of the polar opposite of that in some ways. They're only trying to form edges that have like really short connections.
And then I also really like how you talk about the convergence of search then, and short edges leads to fast convergence, whereas long range edges. And then I think in maybe previewing ahead in the experimental results, I think pyNNDescent was didn't perform as well. Do you think it's because of this lack of long range edges? And maybe the question is more broadly, how do you view long range edges in proximity graphs?
Yeah, that's a great question. So pyNNDescent was the only algorithm that we were not actually able to get to scale to a billion size. Um, Most because it's a very memory hungry algorithm. Like taking the two hop neighbors, especially in an undirected graph, it's just a huge amount of memory. So we were not able to get it to scale up to a billion. On the scale of millions to hundreds of millions, it actually performs pretty well. It doesn't perform quite as well as DiskANN, but it does it does beat out, at least in our experiments, we found it to beat out our implementation of HNSW. And I I don't want to say too much about why this is, because I think I have yet to have a super convincing set of experiments. But my thinking on it is that, when you're doing a graph search, you're doing a very sort of greedy search where you just start at your start point, and on every iteration, you hop to the neighbor of your start point that's closest. And this is you can sort of think of this as a two-phase process where sort of in the first phase, you're moving to your local neighborhood in the graph. And then in the second phase, you're actually finding the nearest neighbors among this local neighborhood. And I think one of my takeaways from this project is that the time spent finding the local neighborhood is actually a lot less compute. If you're aiming for something like 80, 90, 99% recall, the time to find the local neighborhood is actually a lot less compute than the time that you spend in the local neighborhood finding the nearest neighbors.
Wow, yeah, I just read. I had read HNSW Finger, which had something about kind of like that upper bound condition on the candidates and the results, and that upper bound distance. And yeah, I think I've seen so many of these like CPU traces. That's like a common thing at Weaviate when you're debugging the core engineering to show these CPU traces of where the time is being spent. And yeah, that's a really
Mhm.
interesting nugget. Super cool. So yeah, I think that's a pretty interesting nugget. The understanding that you have more memory to explore the two hop neighbors because you're increasing the size of the adjacency list. And yeah, I definitely think when we talk about filtered vector search towards the end of the podcast, we'll come back to this topic. But yeah, so it would be really cool to also maybe get a little more light on HCNNG and
Yeah. Yeah. So HCNNG is a super interesting algorithm. So it's based on the idea of performing a hierarchical clustering of your data set. So you could imagine doing like you're starting with a data set that you're trying to build a graph on. You could imagine doing like a very simple hierarchical cluster where, for example, on each round, you just pick two random points and you cluster the points based on whether they're closer to the first point or the second point. So you can do this very simple hierarchical cluster until you get to a leaf size of around 1,000. And then the interesting insight of HCNNG is what they do once you've reached this leaf size. So remember, we're building a graph here, so we can't stay at this clustering step. So what they do at these leaves is they actually build a low degree minimum spanning tree where the edge candidates for you don't need to I guess think too hard about the minimum spanning tree part, but they build a minimum spanning tree. So this is a tree with you could think of this just as a graph with degree at most 3, where the edge candidates for a graph with degree of most 3 that's guaranteed to be connected. You can just think of it as that, where the edge candidates for this MST are these 1,000 x 1,000 potential edges between all of the points in that leaf. Yeah, so does that make sense? So right now we've gotten from clustering to MST at leaf. So now we need to actually talk about how we get from there to a graph.
I guess quickly, so a minimum spanning tree is, yeah, sorry, I'm brushing up on my graph algorithms. It's like it connects all the nodes, right? It's like the minimum path. And then, so when you have a degree is 3 for a minimum spanning tree, that means like one node can't have, more than 3 edges. And is this related to say like max flow, min cut algorithms and how you construct this? Like how much of that comes in?
Um, it's not super related. So it's I guess more related to like shortest path algorithms. So the goal of a min spanning tree is to, if you have a whole bunch of weighted edges, is to construct a tree, and this is like an n-ary tree over all of these edges such that the edge weights of the tree is minimized.
Yeah.
So it's connect. So you have a bunch of edges with weights, and in this case, our weights are the distances between those 2 points. And the goal is to construct an n-ary tree over these points. So it has to be connected such that the total sum of all of the weights is as small as possible.
Oh, fantastic. Yeah, it's so interesting. I guess this like combination of computer science with the A and that, like the way that you integrate it is just remarkable. And yeah, so could we continue on? So now we've got these trees for each of the clusters, and now we're trying to assemble them into a graph.
Yes, yes. So right now what we've got is we've built a cluster. It has leaves of size 1,000, and we have this little low degree graph inside every leaf. Now, of course, if we tried to build all of these into one global graph, it would just not be connected. So the insight of HCNNG is that you replicate this process of clustering 30 to 50, about 30 to 50 times with a different random seed each time. And then you merge all of the edges that you get from all of those clusters, all of those MSTs into one single graph. And this graph, this graph experimentally is very likely to be connected.
And so then do you have some kind of pruning heuristic on how you merge the edges for each of the nodes with each of the clusters? Is that correct understanding?
Um, so the original implementation of HCNNG doesn't really do any sort of pruning. So what you would have is you would have about 30 to 50 clusters where each of them has a max degree of about 3. So the max degree of your graph would be something like 90 to 100, 90 to 150. We did find in our experiments that we did some experiments where we just applied the DiskANN pruning rule to this graph. And I wouldn't say that gave us a small boost in performance. It didn't give us a huge boost though.
Super cool. Okay, so yeah, so I think all that's super interesting. I guess it does motivate maybe working now, kind of coming into the partition based algorithms, and because we have this clustering, and yeah, maybe I think now would be a good time to touch on IVF and maybe the parlay
Yeah,
IVF.
yeah.
Yeah, this one.
Yeah, so if we were to, when we talk about these ANNS graph algorithms, so approximate nearest neighbor graph algorithms, the other method that's most commonly used in this field is I refer to them sort of in a catch-all as partition-based algorithms. And they're sort of very similar to some of these algorithms that you might use in low dimensions. And the idea behind them is super intuitive. So you have some large data set and you're trying to perform nearest neighbor queries on points within the data set. So a really intuitive thing to do is to try to partition this data set into some number of partitions or buckets such that nearby points are likely to be in the same bucket. So now I've taken this, say million sized data set and I've broken it down into maybe 1,000 to 10,000 buckets. And when a query comes in, what you do is perhaps you use something like a representative element of each bucket to pick which buckets are likely to be close to the query. And then you exhaustively search, say, a small number of buckets, maybe like 10 buckets or so. And that's how you would get the nearest neighbors for that query. So that's how they work at sort of the level of the most similarity. There's a lot of different methods that you might use to assign points to buckets, like k-means clustering. You might use something called a locality sensitive hash function, which is a hash function that is likely to assign nearby points to the same bucket. Also maybe sort of hierarchical decompositions. Yeah, but they all share the similarity of, break the data set into partitions, query a small number of partitions.
And I'm just so excited to understand, like, to get your expertise on parallel computing and distributed computing with this kind of algorithm. I've towards the end of our podcast with Aditya Kusapati, he was discussing like an end-to-end differentiable index where you learn the embeddings as well as the index to try to like perfectly partition it. And maybe Carnegie Mellon reminds me of Andy Pavlo, and he has a lot of
Yeah.
lectures about yeah, he's great about like with query planning, you say like, where is the data located? And so I think, yeah, so I'd love to understand how you see these partitioning algorithms with like, physically, where is it? And yeah.
Oh, yeah, that's a good point. So I've mostly worked with algorithms that are just done on the CPU. One thing that is nice about partitioning algorithms is that if you want to do a disk-based algorithm, you can really optimize very nicely for your disk fetches by ordering the points such that points in the same partition are next to each other, and you get just awesome locality there. And I think we don't know anything close about how to do that for graphs. So that's something really nice about these algorithms, just that like ability to reorder and have locality. Um, on the algorithmic side, something I'd say about these methods. This is getting maybe a little bit more into like my own opinion. But I think the thing that's really tough about these bucketing algorithms is that if you imagine doing them in something like 2 dimensions, if we just quickly imagine like partitioning a 2-dimensional space, if you have a query that comes in, it can actually only be adjacent to like a very small number of partitions. Probably, I think it's something like 9 at the very most. Because if you could imagine like the query falling into sort of one partition box, and then there's like maybe if you've partitioned them all into the same size, there could be like only a very small number bordering that box. But in high dimensions, that that sort of locality, you think of the number of buckets that a query could be adjacent to, is just really huge. It goes up according to this factor of like 2 to the d.
Wow, yeah, that's that's really fascinating. I guess this is kind of another question that I've asked many times and haven't quite been able to wrap my head around it, but it's kind of like how DiskANN uses the disk. And I thought there was some kind of clustering in there as well, where there's like a clustering in like a graph per cluster, but it sounds like the graph per cluster thing, it doesn't work in high dimensions. Is that?
I think that one works all right. I'm not so ParlayANN doesn't do disk-based algorithms. So I think in the original DiskANN paper, so it's a little confusing. Sometimes people use DiskANN to refer to the whole system that works on the disk, and sometimes people just use DiskANN to refer to the algorithm. And I'm mostly using it. I'm mostly using it to refer to the algorithm for making the graph. But yeah, I believe in the original DiskANN paper, part of their strategy to put things on the disk was to shard their data set into something like 30 partitions. I believe they did this with some amount of repetition, and they merged some of the edges at the end. So I think this was to save compute.
Okay. Yes, it's super fascinating. I'll definitely, keep studying DiskANN and trying to understand all these ideas. But awesome. So, could we maybe come now into parallel index construction? You have all
Yeah.
these amazing things like prefix doubling, and yeah, if we could just dive into how this is achieved.
Sure, yeah. So I spoke earlier about the incremental algorithms. And at a very high level, DiskANN and HNSW are both incremental algorithms, and they both have a phase where for a point P that you're inserting, you figure out what points you want to form edges to, and then you add edges back from that point to P. So they both so when it comes to parallelizing these algorithms, they both have this same sort of pain point where there's data races adding edges to vertices that already exist in the graph. So yeah, I'll talk about how we got around that. Yeah, so if you just imagine parallelizing it very naively, you could, for example, throw all of these inserts just into a parallel for loop, and use locks to control any sort of data races. So when those 2 points again are trying to add edges to the same existing vertex. So
Can I
yeah, we
maybe get
didn't
a
really.
quick? Oh, sorry. Can I maybe just get a quick clarification? So when they're trying to add to the same vertex, I would think that the kind of pruning would just like I'm not like it's probably just me, but like I'm not quite understanding the problem then because so you're trying to connect like B to A, and then C is also waiting to connect to A.
Mhm.
Can you maybe help me understand a little further like what the data race looks like?
Yeah. So let's just say we're doing C++. Okay, so we have this vector. We have this vector. It's like length 64 or whatever. And it has it has like some empty space at the end. So we're all trying to insert into index, say 59 of this vertex. So if process A and process B are both so process A and process B then might both be trying to add themselves to like spot 59 of this vector. And that would cause undefined behavior if you weren't controlling that access in some way.
Oh, okay. Yeah, going into the details. Awesome. Okay, cool. So, yeah, so continuing on from there. So we don't want to have these, data races, locks with trying to add these edges. So instead, you've come up with this like way of batch ordering the inserts. Yeah.
Yeah. So, and then I should also add that, so I mentioned this process of adding back edges. So processes A and B both want to add edges to C. One other thing to keep in mind here is that we do want to be keeping a degree bound on the graph because we can't just let this graph have like unbounded degree. We don't have the memory for that. So we keep some sort of degree bound. You can think of it as about like say 64 or so. So when existing processes try to add edges to a vertex, if they would add edges such that it would exceed this 64, then we have to apply a pruning procedure. So that's sort of the other piece of what's going on here. So then let's get into the parallelization. So we use this idea from parallel algorithms that's called prefix doubling. It's sort of a technique that can apply to parallelizing a lot of these incremental algorithms. And the idea is that we could insert without locks by inserting in doubling batch sizes. So you first insert, say, one vertex in the graph, then you insert a batch of 2, then a batch of 4, then 8, then so on, up until a max batch size of maybe 100,000 to 1,000,000. And what we do, so let's dive into exactly how we do a batch without locks, because I think it might not make sense yet. So we have this, so we have this batch, let's say it's V20 to V25. And we first determine the edges that we want to add as the out neighbors. So these are directed edges. So the out neighbors of V20 to V25. And we can do this in parallel just fine, because this is just done via reads of everything that's in the existing graph. So now we need to come to the point that now that we've determined these out edges, we need to add reverse edges. So we need to add edges from existing vertices in the graph to these new points so that they're reachable. That's the part where we have data races. So what we do is we collect up all of the edges that we want to add to the graph in parallel. So we've basically taken all of our new edges and we just reverse them. We collect up that we collect up that array of new edges all in parallel. Then we sort it based on which vertex you're trying to form an edge to. So at first we just had sort of this unsorted array of reversed edges, and now we sort them based on the vertex they're trying to add to. So this would be the part where if A and B are both trying to add an edge to C, those edges would then end up grouped together. And then independently in parallel over all of the vertices we're trying to add edges to, we do the pruning procedure. And this is done on copies of the edge data. So we're not like actually modifying the graph yet. That's kind of important. So we've taken so for every vertex C for which we're trying to add edges to, we take a copy of its existing edges. We merge those with the edges that we're trying to add. We prune them. This is all done in parallel over all of these vertices C. And then at the very end, we do one write to the graph where we give all of these vertices their new edges.
Yeah. One of my favorite things about this podcast is recording it, and I know I'm going to listen back to this quite a few times. And yeah, it's such a fascinating way of doing this. I guess maybe there are all these little details that I think just each one adds up to it. I like the the semi-sort, the way that you group together the B to A, C to A, if I can keep using that example, and yeah, it all is just such a fascinating algorithm. I guess I don't really have any. I guess maybe one question from with Weaviate, we're working on something called a dynamic index, where it's basically based on the idea where Weaviate is built for multi-tenancy, where one user only has 100,000 vectors, so we're just brute forcing it until it hits that point, and now we have this kind of batch construct the graph. And so I'm pretty curious about this, I guess I don't really have a question, more so just like I'm like seeing the eureka of understanding this opportunity of how you have this kind of how you do the batch construction and exactly walking through. I think just the detail of like this prefix doubling technique. It's so clever. It's such a clever way of like you're increasing the parallel batch size so that in the case of I think you say in the paper it's like you're only seeing half the graph in one of the batches. And so
yeah, up until you get to sort of your max batch size. And maybe, I could say a little bit about like what's important about the prefix doubling here, which is that, or why we actually chose to do this doubling strategy, which is that, say, imagine you have 10 vertices in the graph, and you want to insert a batch of, say, 50,000. This would go really, really poorly because all of these 50,000 vertices would only form edges to these 10 vertices that are existing in the graph. So this would produce like some monster. So we use the prefix doubling to make sure that the batch is never too large for the size of the graph at the time.
And this is an algorithm that comes from like parallel computing. Is that correct?
Yeah. So this was initially introduced on a paper on parallel incremental algorithms for some geometric problems
Wow.
like solving linear programs.
Yeah.
This was maybe 5 to 10 years ago. So it's been a really versatile technique.
Yeah, and I think that's just like the super 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 remarkable thing about this research is how you are connecting the parallel computing with the ANN as well as the minimum spanning tree and all that. And yeah, so it's all just super fascinating. So now, if we could dive into the experiments and sort of what you found by
Yeah, yeah.
this, yeah.
Yeah, so I can talk about, so in our experiments, we probably had about two main goals. One goal was that we wanted to run all of these algorithms at a billion scale. For context, our lab machine has about a terabyte of RAM and it has 72 cores. So we're looking at running billion size experiments in memory on a machine like this. So that was our first goal. We really felt that I think the community has actually woken up to this a lot. But when I started working on this paper, there was just a real lack of papers that did experiments up to this size. And I would always worry when I read a paper that only worked on, say, graphs of size a million. I would always really worry that they might be missing something because I think the problem is just a lot easier at that scale. And then the other goal was to measure the increase. The other goal was to measure the increase that we got for our parallel builds compared to the parallelism of the existing algorithms.
Yeah, I have some experiments that I'm working on that are at a million scale, and I'm like, oh no, I'll have to redo them.
Oh, I mean, I think I do all my first experiments at a million scale, but I usually don't quite believe myself until I take it to a bigger scale.
Yeah. Oh, yeah. I had noticed this. I've been studying filtered vector search, and I noticed that kind of like a rarely occurring filter thing from 100K to a million. You see the slowdown increase like crazy, and
Yes.
hearing what you're seeing with the QPS scaling logarithmically as at scale. I guess maybe the first question I'd have about these data sets, like the big ANN data set, it comes from SIFT vectors. I haven't
Yes.
been able to find where SIFT is. It ImageNet encoded? ImageNet's not a billion. I haven't been able to figure out where these come from.
Oh, that's a good question. I've always just taken at face value that there was this thing called a SIFT descriptor, and it described how to encode a vector into it, or how to encode an image into a vector.
Yeah, yeah. And so where do you think? So I think in the big ANN competition in NeurIPS that you had participated in, I think won the filtered track, and
Yeah.
so the data sets there are. I think there's something like it's like YFCC.
Yes.
Yeah.
Yeah.
Some,
So, yeah. Would you like me to talk about that competition or?
yeah. I guess just generally thoughts on the data sets used and
Lots on the
yes.
data sets. Yeah. So, I mean, the big ANN competition. So, there was a 2021 one whose focus was on billion size vector search. And they had about 6 billion size data sets. I believe maybe two or three of them were released just for the competition. So the organizers of that competition, like, I think did so much for research in that field by releasing these billion size data sets and really creating that encouragement. And then in 2023, they did another competition that had about four tracks. I think one of them was out of distribution, one of them was sparse, one of them was filtered, and then one of them was dynamic. But yeah, I'll talk about the filter track a little bit. So the goal there was to do nearest neighbor search, but on vectors that also satisfied some sort of arbitrary Boolean predicate. So I guess the quintessential example is like I'm shopping on Amazon and I want shoes. So it's got to be a shoe, but I also want it to be pink, and maybe I also want it to be size 6, and I don't want it to have too big a heel. So you can add all of these you can translate all of these into like binary predicates. So I guess what I was saying was something like an and of like 4 vectors. So that really prunes down the search space of a large set of vectors.
Yeah, and maybe even we could start, we continue into filtered search and IVF squared, and then maybe come back into the data sets if we want. Because, yeah,
Great.
this idea of the predicate, it only lets, yeah, it's apparel, it's shoes, it's pink, and then currently we have this solution called pre-filtering, where what we do
Right.
is we're traversing the graph, and you can come into the candidate set if you don't pass the filter, but you can't come into the result set if you don't. And this results in a lot of backtracking. And so this is one of the big outstanding problems in approximate nearest neighbor science. And you've developed this algorithm IVF squared to solve this. Can you maybe explain that further?
Yeah, yeah. So this is sort of after, this is sort of after the ParlayANN. We worked on a slightly different team. This team on filtered search was headed by Ben Landrum, who is a master's student at UMD, and he's about to start his PhD at Cornell. So he was really the leader of this project. He did a great job. So we wanted to look at this problem of filtered search. And the problem with the thing that's difficult about using graphs for filtered search is that if you just have one graph over the entire data set, but the actual only possible candidates for your vector search are a very small subset of the graph vertices because of this predicate that you've added. You can imagine just having a graph where I put yes and no over all the vertices, and the yes is just this very tiny subset. So it can be really hard this yes is just this very tiny subset, but it also might not have that much relation to the actual distances. Like as in points that are both yeses might not actually be close to each other. That's kind of the hard part, and that's why the nearest neighbor search that's why the traditional nearest neighbor search doesn't work so well on it. What we did in our IVF squared is we looked at this problem where it was very hard to do filtered search on a general nearest neighbor search graph. And we basically asked the question of, okay, what if we actually just break all of the points up according to their filters? So I should say a little bit more about what the data set is like. So this data set, YFCC, it had about 10 million points. And it had, I think, maybe about 1 million unique filters. So these are a million different attributes for which I could have that yes or no.
Wow. Yeah.
Yeah, so it's a lot. And each point had on average, so these million can all overlap. So each point on average was a yes each point on average had about 10 of these filter attributes attached to it. So not every point had every filter attribute attached. So what we did, our insight was that you could build an inverted file index where you built one nearest neighbor index for every single filter. So if I had a filter for shoe size, all of the points that had that label shoe size attached to them would be in one index. And then maybe I have a filter for pink, and all of the points that have this label pink attached to them, they make one index. So what we have then is a whole bunch of nearest neighbor indices. And we realized they're actually on like a super skewed distribution as well. So most of these indices only had something like 10 to 1,000 points in them. So brute force search, totally A-okay. And then some of them were a lot bigger. Some of them had hundreds of thousands to maybe about 1 million points. And under the hood in that inverted file index, we put a nearest neighbor search structure, like a graph, or in some cases, in some cases, a partition. So we were able to split the problem up, into points that satisfied all of these filters. And then we looked at their size under the hood and picked an appropriate structure for them based on that size.
Well, that's perfect with the kind of a dynamic index thinking that we're trying to pursue at Weaviate. And so I guess
Right.
kind of, so that's where the, so that's where the IVF squared thing comes in, where you've partitioned it based on the filter. And then within one of the filters that's say between 100,000 to 1 million nodes, you would have another kind of partition based filter and then beyond. So I guess one question I have with this is, how do you like, I'm very curious about kind of like range filters. So with the shopping example, if the price of the shoes is between $120 and $150, but you sort of like cut up the filters now to be like $120, $121, like you have to think about this kind of bucketing. How do you think? Yeah.
Yeah. So I haven't worked on this. So the competition didn't do this problem. It was just binary filters. They were just yes, no. But I have some colleagues at MIT, and I believe Ben, that same master's student, was on this project about range filtering, and they found a very clever solution to this problem. So to be a little more clear, like we're talking about binary filters specifically before. Okay, is it pink or isn't it? But now we're talking about range filters. So maybe I want to find something that costs between $25 and $50, or maybe I want to find something that costs between 50 and 150. So this is kind of a different type of filter. They had a really interesting solution where they built overlapping nearest neighbor indices. So they would, let's say your price range is 0 to 150. So they built one index that's like 0 to 150. But then they also built two smaller indices, one for like 0 to 75, and then one for 75 to 150,
Mm.
and sort of keeping this process up recursively, so that when a range query came in, you could pick like a subset of these sub indices that would cover your whole range and query all of them. So it was a very clever design.
That kind of reminds me of this like self-driving database kind of idea where it's like you're seeing what particular kind of range queries are coming in, and that helps inform you on which sort of partitions to build. Eh, yeah, cool, cool, cool. So another question I have, so there's this new algorithm called ACORN for solving filtered search with proximity algorithms, where basically you connect the two hop neighbors, so the pruning heuristic is changed a bit, and then the way that you do the pre-filtering is changed, where you'll get the neighbors of a node, and then you filter it based on if they have the filter membership. So I guess kind of generally, I'd like to ask this question of what do you think about supporting, arbitrary filters, all this kind of stuff with proximity graph techniques?
With proximity graphs, I think it's really hard actually.
Yeah.
Filter DiskANN does a great job of showing how you can adapt like a DiskANN graph to answer single filter queries. I think when it comes to like totally arbitrary predicates, where like a totally, a very small and very random subset of the graph could be anything, could be all you're allowed to report for your answer. Um, Honestly, I think that's really hard. I think it's an open question whether a single graph based approach could work for this, or whether you're going to have to do some sort of partitioning via your labels. I think we in Parlay IVF, IVF squared, I think we came up with a nice solution for that seemed to be capable of answering up to 3 conjunctions of labels. I think when you get to more, it's still super open. I think hopefully, I know lots of people are working on this, so I'm interested to see what happens. But yeah, I think there's a lot to do there.
Yeah, and I have one more question on this. This is kind of related to what I asked you at MIT, but I think I didn't really format it right, and I was trying to make it more general. And is this idea of something that I found to work is after I build the HNSW graph, I then apply a filtered search for the rarely occurring filters, and then I'll add those neighbors. And, and so I'm thinking this is kind of like I like calling it graph repair.
Yeah.
Because I
Yeah,
think
this is like I guess this seems sort of similar to filtered DiskANN, but maybe like in sort of the opposite order. Because I guess what they
mm,
do is they partition based on the filter. They build graphs based on each filter, and then they merge them all together. And I guess you're sort of doing that, but like after the fact. I think it's been shown that that can work really well for single filter queries. Um, I think when it comes to arbitrary predicates, where maybe sort of
mm.
each vertex of the graph could be in something like exponentially many number of filter queries, I'm not so sure whether that could work. But yeah, for like single filter or maybe 2 filters, I think that approach seems very promising.
Yeah, I don't the arbitrary filter idea. I'm not sure.
I know. I think nobody knows. I think nobody really knows how to do that yet.
It maybe reminds me of the kind of I love that self-driving database. I love like OtterTune. Come back to Andy and Carnegie Mellon is like that. You see the query workload, and so that kind of informs you on what sort of special indexes to build. And I think maybe that. kind of thinking helps with the arbitrary filters. And but yeah, it's
Mm,
also interesting. So I think this kind of transitions nicely as well to this sort of out of distribution query thing. We talked earlier a bit about the binary filters. Like I don't know if it applies with shoes. Like if an embedding is pink, like maybe the nearest neighbors are also pink, but maybe the filter is like what time it came into the store, so it's like totally unrelated to the embedding. And
right, right.
I'd love to just learn more about how you understand this out of distribution problem. It sounds like multimodal is people think. Yeah.
Yeah. So I guess the multimodal problem, it's related. I usually think of it a little bit differently. Um so you're right though that it's very related to this idea of sort of having a label on your point that's a little bit arbitrary and not so related to the actual Euclidean distances or whatever. Um the out of distribution case that I've looked at the most has been data sets where the embeddings are generated from some sort of object like an image, and then the queries are generated from a very different sort of object. So the quintessential example is text to image, where the embeddings are based on image encodings, and the queries are based on text encodings.
Hmm.
And if you look at searching the image database with the image encodings, that's just so much easier than searching the image database with the text encodings. The embeddings they just don't seem to talk to each other as well.
Hmm. Yeah, it's I haven't really started thinking too much about it to have a fully formed view on it, but this like distribution shift and how that might, I think distribution shift is something that machine learning is always worried about, and thinking
Yeah.
about how that might impact these neighborhoods of these graphs because it's like connected for a particular sort of like vector space that they've
Right,
seen.
right.
Yeah,
Yeah,
yeah.
so we've had some amount of success adapting graph-based algorithms for this out of distribution by doing things like taking a sample of your query distribution and trying to use it to influence you could imagine building your graph on the points that you want to search, but maybe also adding some of these extra points from the query distribution. You wouldn't report them as answers, but you could like embed them in the graph in the hopes that they would sort of influence the edges of the graph to be a little bit more amenable to that distribution.
Huh.
So we've had some success in getting better recall doing things like that.
Yeah, that's
But I
amazing.
think
Yeah.
it's still quite a bit harder.
Hmm. It kind of like the navigable small world graph thing about like how many hops are you to Obama is kind of like the motivation behind these graphs. And yeah, that idea of adding some nodes in there that like better connect it because they're more in line with the distribution, that is so fast. And I think we're also seeing this wave of like using LLMs to generate synthetic queries for documents, like in that particular kind of like text retrieval setting, RAG. And so that kind of like generate a query to put it in the graph, and then that's really a fascinating idea. Super cool. I guess maybe another quick. Well, I also wanted to, because you've outlined some future research interests that I think obviously you have such insight into this. And could you also tell us about dynamic graph based ANS algorithms that can update without locks? Yeah, and so yeah, I guess dynamic meaning insert versus batch. Is that correct?
So I guess when I talk about a dynamic algorithm, I usually mean an algorithm that can take both inserts and deletes to the data structure. So what
Mm.
I want to do is do both inserts and deletes. So if you take an algorithm like DiskANN, so DiskANN had a follow-up paper, Fresh DiskANN, where they showed, so the algorithm is incremental,
Mm.
so the inserts sort of come like for free anyway, but the hard part is how you do the deletes. And they showed a very nice algorithm for how you can do deletions and come up with a graph at the end that has just as good recall as the graph before you did the deletions. So one of the big projects that I'm working on right now is I did this project on ParlayANN where I showed how to build these graphs statically without locks. But I also want to take this to the dynamic case. So in the dynamic case, of course, you're going to have some sort of concurrency control. Um, but what I yeah, sorry, that might not have made so much sense.
Oh no,
Um,
sorry. I'm just when you I've been learning so much in this past, like, five, like, just recently. I've been aware of your work for a long time, but this last bit of just studying it and seeing all this parallel computing concurrency, it just, my brain is like going into that space of preparing for what you're about to.
Yeah. Yeah. So the goal here is actually to have a dynamic ANNS graph that can serve queries concurrently with updates. So previously, I was just talking about a static graph. So you build it, then you're done. Now it's time to do updates. But here I'm talking about you have inserts, deletes, and queries coming in all of the time, and you actually want to serve all of them. And importantly, queries really have to be still happening while you are doing the compute for the
Mm,
updates,
yeah.
because otherwise the latency would just be unacceptable. So I'm working on this actively, but I'm working on doing this dynamically from a sort of versioning perspective. So the idea would be that you have an ANNS graph, and you have it at like time t0. But then some updates come in and you have a version of the graph at time t1. So some of the edges are different. And the basic idea is that when queries are coming in while I'm creating this version T1, the queries will see this version T0. They'll
Mm,
do all of their queries on T0 while I'm making T1, also sort of in the background. And then once I've finished with graph T1, I will, I will sort of post this version in terms of the diff of the old edges versus the new edges. Say, okay, T1 is now online. Maybe now I'm going to start working on T2 in the background, but
mhm.
queries are going to go to T1. So yeah, I'm looking at using versioning as a way to um, get this concurrency, get queries happening at the same time as updates, but still at the same time without having to use concurrency controls like locks.
Amazing. And yeah, I think earlier mentioning the dynamic index at Weaviate and how we have this kind of like asynchronous indexing where get the vectors into Weaviate and we'll brute force the index queue while we're building the thing in the background. And it's just really exciting hearing that you're pioneering future research on that. And then hopefully we can, add it to Weaviate.
Yeah, I hope so.
Yeah, yeah. Amazing. Magdalen, so sort of a concluding question I ask often on the podcast with, world's top scientists such as yourself is, what directions of the future excite you the most?
That's a great question. Um, So I think something that I haven't mentioned that has been on my mind. So we haven't really talked about quantization at all.
Oh,
It's not really my like particular forte. But I think I've talked about how to build these dynamic ANNS graphs. But one thing that seems to be a big problem on the horizon is that sometimes you'll compute like a vector quantization, and then you'll have vectors come in and the distribution will change and your quantization won't be so good anymore.
mm.
So I think, yeah, figuring out how to update your quantization online, that's in addition to like the filtering and out of distribution and dynamic. That's a problem that I see becoming bigger and bigger. That's a problem that I definitely want to solve.
And that also, so fitting the k-mean centroids, how is parallelizing that? I think you have to. All right, I'm gonna remember the k-means is kind of like you're computing the distance to the centroid, and then you recalculate the centroid, so you could parallelize the distances to all the centroids. Then I guess you need to sync it up to update the centroids, or is it like, yeah?
Yeah, I think paralyzing k-means is not too bad. I had colleagues who worked on it last summer. I think they put. I'm not sure. I don't know the nitty gritty details on that one, but I think paralyzing k-means worked out pretty well. I think it's one of those things where paralyzing the static algorithm is not too bad, but paralyzing the dynamic algorithm might be quite a bit harder. And especially when you're coming to a quantization, especially when you're looking at something like quantization, where you have a bunch of old vectors where you've already like done the work to do their quantization. And you maybe want to try to you maybe want to bootstrap it. You maybe don't want to have to recalculate it from you maybe don't want to have to like recalculate their quantization using the full precision vectors from the ground up. So I think like having a quantization that could actually adapt without actually having to sort of re-quantize the whole index from scratch. That would be a fantastic thing if we had that.
Yeah, it sounds remarkable. I'm also really curious what you think about maybe like TS&E style compression, or maybe fitting an autoencoder machine learning model to compress, and I guess, yeah, like maybe so quantization outside of k-means, because I haven't done any experiments to see like if TS&E, when you do, or like PCA, if this kind of like orthogonal variance of the data compression, if that also preserves like distance for the sake of uh, vector distance, and of course what we've been talking about. And then I think with the autoencoder, I'm not sure if it seems like the embedding model providers are already trying to compress it as much as they can, and they preserve that contrastive loss. And yeah, I'm not sure that's the most well-formed question. I think actually maybe a question I'd rather ask is what you think about using GPU computing for quantization, and I guess like sorry this is going all over the place, but generally this GPU, it offers like massive parallelization, correct? I
Yeah,
just love,
yeah.
yeah.
Yeah, so I think quantization, especially quantization, I'm yeah, I mean, I know that I know that it can work very well to run machine learning models and generate embeddings on GPUs. I think it can also work quite well to do um, quantization or IVF on a GPU. So I think those are really, yeah, I think those are really great avenues for, I think those are really great avenues for GPUs. That's not something I've worked on myself. But I think FACE, for example, has a great paper on how to do both quantization and partitioning on a GPU. I think it's actually graphs that are a lot harder to do on GPUs, because the workload there has like so little locality.
Hmm. I don't mean to be, critical of like the Cagra Rapids vector index, but it doesn't look to be so much faster. And now you're asking for a GPU, so I haven't really crossed the threshold myself into really looking heavily into GPU methods for ANN. And it sounds like you have.
Yeah, I haven't so much either. I'm aware of I'm certainly aware that Face like gets great performance on GPUs, especially compared to their CPU performance. Um, as far as I know, I think for graphs we're not that close to the GPU matching the CPU.
Would it be an idea to like build these indexes with GPUs, and then you can just move the index to a CPU, or like these kind of hyper-threaded machines as well?
Yeah, that could possibly work. I That might actually work better for I might be a little bit skeptical for methods like DiskANN and HNSW, because their build has basically the same workload as the searches. You're just doing like a lot of random accesses to the graph. I might be more optimistic about a method like HCNNG, since you could you could order the data like according to the hierarchical clustering, um, and you could have a lot of you could have a lot of locality there, like while you're building those MSTs. That might be something that might work very well to build. That might be something that might work better to build on a GPU, and then you would. I would guess you might want to migrate it to the CPU after building for the search, because then you're right back into that like very random workload.
Yeah, amazing. Magdalen, thank you so much for joining the Weaviate podcast. I can't even tell you how much I've learned from just like our collaborating here and studying your works further. This intersection between parallel computing and these ANN algorithms, all the experiments you've done with ParlayANN and your team with ParlayIVF, the IVF squared, and all this amazing stuff. It's been so cool meeting you, Magdalen. Thank you so much.
Oh, yeah. Thank you. It was great to meet you too. Thank you for having me. It was so fun.